So we I think it's nicer if you write in lines. So we just do the lines. So let's look at a um, recap of beam design. So we have two main types of beams. So we have simply supported, as you've seen. Okay. And then we have the continuous beams. So with the simply supported, you analyze it just like what we did in the basic structures, right? So you find your reactions, you find your bending moments, your shear force diagrams, and then you use them to design the structure, right? With the continuous beams, there are two methods. If you have the case whereby span length, so span length equal, and then so if certain conditions are met, so let me just start it this way. Let me do that. So the first scenario is that you have a case whereby you just use a general analysis process. So whether it's slope deflection method or moment distribution, or three-moment equation or the force method, whichever method you want to use, you can use that to determine the forces and then, there find the reactions and then draw your shear force and bending moment diagram. Right? That's what you do for a typical continuous beams. All right. But we can also so we can so use let me say general analysis process. All right. Okay. Then here we use what word should I look for? Should I call them factors? Yeah. So let's we use factors. I mean, not the right word. I'm trying to look for the right word as we go along to see which word which word will be appropriate to describe what I'm trying to arrive at. If you remember, last week, okay, I think the word is coefficient. So using coefficients, so using bending moment and shear force coefficient. Okay, so we realized that last week when we were looking at beams, we mentioned that if the beams have of a continuous beam, if it has equal spans, and then the life load QK does not exceed the dead load GK, then we can use these coefficients. All right. So there are some conditions that your beam should first meet before you can use any of these. Uh, any of these coefficient. I mean, this coefficient option that we have. All right. So if the conditions are not met, then you have to go through the first principles calculation process. All right. They can use that to design the beam either for both shear and then uh, bending. All right. So that's basically what we're looking at. And then again, when you are dealing with design, you check if so for bending design, which is moment design, you check for whether it is only tension, rebar only, or you need both tension and compression rebar. So check whether it's one of the two, and that will depend on the kind of moments that we have And then for shear design, right, you check if you don't need any shear links or whether you need only nominal or you actually need shear links. Okay. So a beam can have all three. So it can have the case whereby some parts need shear links, some parts will need only nominal links, and some parts will not need links at all. Or it can only have two, where some parts need shear links and nominal links, or either one of these. Okay, and this is what goes into a typical beam design. All right. So before we design for bending and shear, we should have done the analysis. We should say that to, typically to get your shear force diagram and then your bending moment diagram. Okay. Um, I think that's um, that's all that we have so far with regards to the beams. All right. Um, Let me make sure that is working. Right. So this is what we have with regards to the beams. Okay. Now let's look at another structural member. Okay. Let's call it design of slabs. Okay. Uh, Let me put this into a bracket so that it's guys sets. Generally, the design of slabs is similar to beams. Okay, it's similar. So let me put the word similar into quote. Right. At least let's have that in there so that everything will come full circle as we look at the process. So let's look at slabs. All right. We have we through engineering drawing, I think with cat two or so, we looked at what slabs were. And one of the things that we um, looked at when it came to slabs was that they are, should I say, typically they are found on the um, just give me a second. So when you look at slabs, so if you have a panel, sorry, structural member, right, that looks like this form. Now, if this is the width B, maybe there's a length L, and this is the height H. That's a bad way to show the height. Sorry. Let me make sure that this thing looks good. Okay, this is the best I can get it to be. Fine. Let's say we have this height H. This is our height. Oops, wrong color. Let me use a green. It's a terrible green. So this one should work. Great. So this is the height H. Okay. Where your L and B are very large compared to your height, then this defines it as a slab. All right. So they're usually horizontal flat face panels, whereby the plan length or the plan area or the dimensions of the plan are very high compared to the elevation or the vertical elevation, right? And We also know that slabs generally they can be solid. So we have solid slabs. Uh, they can have ribs or they can be ribbed, and then we can even have waffle slabs. Um, then we have the what's the name? We also have the flat slabs. All right, which are the special types of slabs. Right. So these are some examples of slabs. A typical solid slab. Uh, so a typical solid slab would look this way. So you have a slab. Okay. Then you also have your beams. I'm supposed to draw this one to look straight. So I'm just draw them straight, straight. Okay. Okay. So it becomes a series of crisscrossing of beams. Okay. So that's a typical flat slab. Sorry, a typical solid slab. Okay. So in plan, if this is your slab in plan, then you have your beams looking this way. All right. So they can be in this one direction, or you can have a series of crisscrossing beams. So this is a typical solid slab. This is how mostly we are constructing structures, we use these types of slabs. All right. For the solid slabs, we also have um, the what's the name? The waffle slab, for example, um, which so the with the waffle slab or the sorry. So the waffle slab, I'm just show us how it looks like. All right. It's not too common, but we do have it. Okay. So what happens is that we have the main beams. So if this is your slab, um, and draw. So these are the main beams. All right. Let's say there are two more. These are the main beams. So whatever I draw, I'm just drawing them with it with thicker lines. Then in between the main beams, you have smaller beams. Okay. You have these smaller beams. Okay. If the beams are going in one direction, like in this case, so if the smaller beams are moving in one direction, then uh, they are called ripped slabs. Okay. So usually have the slab going one direction, like I mean, sorry, you have the smaller beams or the secondary beams going in one direction. All right. So um, if beams or secondary beams, let me say that one secondary so that it's not the primary beams. If the beams are moving in one direction, then they are called ribbed slabs. Okay. So with the waffle, then it means that we need to have a waffle slab. So let me let me put it this way. Let me make this one rep so that I will just use that option to explain the waffle. So with the waffle slab, the secondary beams are moving in are moving in are by moving in two directions or bi-directional. All right, so in two directions. Yeah, all right. So just take we're gonna take the same drawing that I have over here. That's my funny looking drawing and place it here. Okay. And then what I would do is that I would draw another set of smaller beams going in that direction. So something like this. Okay. So it becomes like a waffle. You know how we have this waffle food that we eat kind of like, is it a pastry? Yeah, kind of with this whole crisscrossing set of lines. That is how the waffle slab also looks like. All right. Then with a flat slab, as the name implies, so in the three previous cases, slabs connect to beams. Okay, take a note. But with a flat slab, the slabs connect to columns directly. Okay, so that's the difference. So usually, if you take a um, flat slab, you'll see that if this is your slab, instead of beams, you see columns straight away. Okay. You see the columns. So here is a slab. Okay. To prevent punching shear, which is one critical failure mode of slabs, we use we can we can change the way the column connects to the slab so that we don't end up with a flat slab situation, right? Um, so to do that, we can use column heads. So instead of the column directly connecting to the what's the name, to the slab, we can actually change the column head. Maybe instead of it coming this way, we can say, okay, then it should bend a little bit so that we increase the surface area that the column would have with connection to. So we can change column heads to reduce or to prevent punching shear failure, which is common with these types of structures, is that we change the column head. So normally the goal is to increase the surface area of the column so that it will reduce the pressure, right? Or we can use what we call drop panels. So we create a small panel and which uh the column will connect to the drop panels, right? To uh, position drop panels. All right. So these are some of the things that we do. So sometimes you go to a place and you see that um what's the name? Either we are using drop panels or we are increasing the column head so that in the effect we can reduce the pressure being applied by the column or the slab and vice versa. Another thing that is critical to slabs has to do with um, how slabs and okay in terms of load distribution. Normally, if you take a typical slab, okay, let's say there are beams at the ends of the slab, so maybe two. Let me change the colors of the beams. So there's normally the beams will be below the slab, so you wouldn't see them. So that's like I normally draw them with hidden lines, right? So there are four beams at the edges of the slab, right? And normally when you are doing design, you would realize that, or even from um, observation, you realize that for a typical classroom, um, the um, what's the name? The the slab is what receives the load, right? It's like for example, the chairs, the tables, the occupants that go in and out. It's the slab that first receives this load, then it transfers these loads to the beams, right? For a typical solid slab. Once these loads are transferred, or how are these loads transferred to the beams? All right. And that's what we mean by how does the slab span? All right. The spanning of the slab, the term spanning of the slab has to do with how the loads are transferred uh, um, 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 from the slab to the other uh, members. All right. Or how the slab receives the load from, I mean, the occupant, whether it's dead load, live load, so whatsoever. All right. And that will determine how we design the slabs. All right. So if this is your length in the x direction, and this is your length in the y direction. All right. We have to find a ratio of the two, Lx over Ly. If Lx over Ly is more than 2, then your slab spans in one direction. Okay. And normally the loads are distributed to the ends or to the Lx ends. All right. So loads are distributed to the longer edge. Okay. Let me say usually, because sometimes you can force it to distribute the loads to the shorter edges. But by convention, the loads are typically distributed to the longer edges. So it means that um, for a system like this, we have two long edges, or we have beam. So this is beam one, and this is beam two. Okay. So we can divide our loads into two. Okay. Once Lx is more than Ly, it doesn't matter uh, what we do, right? Please, the Lx is always the longer side. It doesn't mean the horizontal side. So I can have a beam like this, and then maybe this could be my Ly, and this could be my Lx, and it's the longer side over the shorter side, please. All right, so let me put it this way: longer side divided by shorter side, not necessarily Lx over Ly. So I think some books will prefer to go with this approach. I think I've seen some books like that. It's fine. The idea is that the longer side should be divided by the shorter side. Please take note. Okay. So what this means is that whatever load comes onto the slab, half is given to beam one, and then half is given to beam two. All right. And we use the sign to represent panning in one direction. Okay. So the sign here, this represents panning in one direction. So one, I will say one way span, one way spanning in terms of the load. Now, there's also another option we can look at. If you have a slab, okay, so let me call this one the same thing. This is my LX, this is my LY. Okay. Now, again, it's longer side divided by shorter side, please. So longer side divided by shorter side. So this becomes what? So again, your LX, assuming your LX is your longer side, your LY is your shorter side. If this is less than or equal to 2, then we see that the slab spans in two directions. All right. And this is important to us, which means that if there are beams on, let's say in this case, these four edges, so we have these four sets of beams, it means that each beam will receive some of the load coming from the slab, and what portion of loads depends on the dimensions of the slab. All right. So L um if LX is more than LY, we'll end up with this division. Let me see if I can draw. Yeah. So we have some of the load going to the beam here, some coming to the beam over here, some coming to the beam, and some coming to the beam, right? So the shorter side will normally receive triangular loads, all right? So the shorter side usually receives triangular loads, and then the longer side usually receives the trapezoidal. And if they are equal, if LX is equal to LY, then the loads will be triangular for all four. Okay. I was going to say something. Yeah. So the uh, this is a for symbol for two-way. Okay, two-way or two direction spanning. So you pick some books and they have this diagram right here. Okay, so take a note of that. And this is important to what we do over here. Right. Um, So sometimes, when it comes to options with regards to slab design, all right. So options with regards to slab design, it depends on how the slab is positioned, right? Just like beams, we can also have simply supported. So simply supported, and then simply supported, we can have one way and have two way. All right. Then we can have continuous slabs. Okay. Again, we can have one way and have two way. So that's the spanning or the directions in which they work in. And there's a third one. It works with the continuous slabs, all right. But I call it panel slab, right? I would explain all the three concepts, and these are my own terms, right? To make the learning process easier. And then the panel slabs, I mean, they work under the continuous slab. So let me highlight this one as A, B. Let me call this one B, I, or B, I, right? And they also can be in one way and then two way. So just take note of it. So how do we have simply supported slab, right? Um, so going back to whatever we had at the beginning, um, let's see. If so, let's see. So for a speaker one way, let me call this one A. If it's simply supported slab. Okay. If it's one way, you would realize that this is how a typical one-way slab would look like. Okay. So normally the loads get transferred the the beams on the longer edge. All right, because maybe your LX is more than your LY. Or the when you find the ratio of LX over LY, it gives you more than two. Right? Some people say LY over LX. It doesn't matter. The key thing is that the numerator is supposed to be the longer side, and then the denominator is the shorter side. Okay. So here the beams are at the ends of the slab. We don't have slabs going beyond it. So that is like simply supported. So this is one way. Okay. Then for a two-way, it's still simply supported. That means that for that one, your LX over LY is less than or equal to 2. So again, you divide the loads among the four beams at the end of the beam. Okay. So let's just take note of that. So here our load distribution goes this way. Here maybe it goes that way. Okay. So in this case, you have some of the load. So with this one, this is where our load distribution goes in this form. Okay. And then this is the way we represent it. For this guy, we go that way. Okay. We can have maybe some of the load coming to this guy here. So the beam will receive this load. Then this other beam also receive some similar set of loads. Then this will also receive another set of loads. Okay. And we have maybe another. Let me just change the color. Maybe put some other different sets of notes over here. Okay, yeah. So that is what goes into the one-way uh, slabs. Now with the two-way slabs, it works the same way as the one-way, but usually what happens is that you could, yeah. So that's how come I'll say that the panel slab is, it's under the continuous slab. Okay, so normally what it means is that you have slabs and beams forming a continuous system. So you could have so let's say continuous slab. So um, I could have this slab, all right. Um, Let me extend this line a little bit. Okay, all right. So if I take, let me, sorry, I have to draw it in such a way that I get what I want. So let's say this is a slab with a series of beams. Yeah, so we have these beams. We also have these long beams going all the way to the end. So if you look at it, we call each section a panel. So this is panel one. This is or each area, sorry, panel two. So the area in between what's the name? A set of uh, beams are called panels. So this is panel one, panel two, panel three. So for each panel, you check their, let's say LX1, LX2, LX3. Let's assume that the height LY is the same for all of them. So if your LX1 over LY is more than 2, then your LX2 over LY is more than 2, and then your LX3 over LY is also more than 2, then you have a one-way continuous slab. So you have a one-way continuous slab system. Okay. Because what this means is that if you divide your panel into two, your loads, all of these loads will, oops, all of the loads up here will go to the beam at the top. Then half of the other load will go to the beams below. Okay. Let me change the color. No, no, oops. Okay, great. So the other half will go to this. Yeah, this is a better color. It doesn't change the color of the right half. So you have a system just like a continuous beam, right? So you have a system like this. Oops. So here it's a slab, all right, and then the supports are the beams. So you have your load acting on it. Okay, and this is it. So if the spans are the same, if the loading satisfy certain conditions, then we can use coefficients for bending and shear to calculate the exact shear force and bending moments in the structure. Okay. So this is a continuous slab with a one-way configuration. You can also have a continuous slab with a two-way configuration. And that's when we have the panels and base system, right? Let's say you have, maybe let me just use a ruler. Maybe I can make it look more. So let's say we have a system in place. I'm just gonna waste a bit of time. It's fine. Okay. So let's see. All right. So that is like a big slab, and then it has a series of. Let me just see what I can do with what I have. Interested. Right, so let's say I have these uh, beams. Um, all right. So I'm just drawing a series of beams. Normally, this always takes time. I don't know why. They do. Unless maybe have one here. My views are not of the same um, dimensions. That's fine. Now let's convert this one to the. Let's move to horizontal. Okay. Let's change the color. Maybe use green or something. Okay. Let's move somewhere middle part. Okay. So I think this is okay. Oops. Okay. So these are like this looks fine. I mean, we can manage with this information. All right. So we have all of these nicely drawn. Yeah. So each square is a panel. So these are panels. Okay, so this is a panel, a panel, panel, and a panel. All right. An entire set of panel along one length is called a beam. So this entire zone here is what we'll call a beam. Okay. So sometimes you can have a series of slabs with a panel system, and then you see this black lines drawn like that. Okay. When you see this black lines drawn instead of crossing or cross-like lines, this indicates that you're looking at what? A void. Okay. So this indicates that you're looking at, so this is a void, which is that it is an opening in the slab or an opening in the structure. Okay. And that's usually, if you look at, so you have your LX1, LX2, LX3, LY1, LY2, LY3. So you find the ratios of all of these. And normally the ratios will be less than or equal to 2. So if they are less than and equal to 2, what this simply means is that then you are looking at a two-way system. So this is a two-way, this becomes a two-way uh, continuous slab. And the reason why we are going through all this approach is because of the fact that their analysis, uh, it's slightly different. How to get your bending moments and shear forces are slightly different. That is the only difference between the two. But in terms of the design, finding your area of steel required and your shear if there's a need for one is largely the same. So the analysis, so let me just put that into writing here. Analysis of the above um, can vary yeah, because of the load. Because the loads, because of loads one, the distribution directions of the load, um, and then and sizes of the panels. Okay, right. So somewhat it is easier to analyze slabs than beams, right? There are a few reasons why, right? I think I mentioned at the beginning that largely slab design is similar to that of beams. There isn't anything crazy. It's just that sometimes the analysis component is what might cause a bit of confusion here and there, but largely the analysis process is the same. I mean the design process is the same. All right. So, um, concrete slabs, so small. Um, so they behave primarily as flexural beams. All right. So just like beams. All right. So design is similar to beams. Okay. Um, the key thing about slabs is that because slabs are usually their breadth or their width is very large, right? With beams, their width is like 300 millimeters, 250 millimeters, 20 millimeters, worst case scenario, 400 millimeters, and stuff like that. With a slab, the width can go as far as 3 meters, 4 meters, 5 meters. All right. So which one do we use? Okay. And the code stipulates that the um, the breadth or the width of slabs um, is usually fixed regardless of the size of the slab, and it's assumed to be 1 meter. All right. Um, the 1 meter is 1,000 millimeters. Okay. So pretty much everything that we design or we calculate is to a meter length, all right, width of the slab. Okay. And normally you would realize that because of the thickness of slabs, the shear stresses are usually low, very low. Shear stresses are low in slabs. Okay. I mean, usually it's not always the case, so just take note of it. Uh, and slabs. All right. So except where we have concentrated load, okay, where we where we have heavy concentrated loads. So take note of that. All right. Um, and again, also, you realize that compression reinforcement is rarely used, okay, or required. So because of that, slab design is much more a straightforward process as compared to that of the what's the name? To beams, right? Because most of the time you have a fixed width, perimeter width. You have the case whereby shear stresses are very low. Because you have very low shear stresses, you likely will not do shear design, except where you have very heavy concentrated loads. An example could be maybe there's a large equipment sitting right on the slab. All right. This large equipment will definitely provide some bit of a bit of high load concentration at that particular point. All right. Then also, you hardly have a need for compression reinforcement. So I think compression reinforcement is rarely required. Okay. Um, so let's see which of these methods, I mean, we've discussed like at length what goes into slabs. So let's see how we can analyze slabs. We can look at the um, so I think before we talk about the approaches, let me talk about a key component of slab design, which has to do with the span to depth ratio. Okay. So let's look at the span to depth ratio. Mm, so let me say effective depth, because it's not just the depth, so it's effective. Okay. Before they come across effective depth already, when we're dealing with the beams, and that is supposed to be the distance from the center of the tension rebar to the top compression flange, right, of the beam. Okay. Um, so span to effective depth ratio. All right. And why this critical to us? Why do we have to limit the depth of the slab with respect to its span? How long? I mean, the distance between the support, which in this case are likely to be beams, is that if you have any excessive deflection in slabs, um, certain deflection in slabs can do what? They can damage, for example, They can damage um, the ceiling, for example. They can damage floor finishes. And then in some cases, some architectural detailing. So let's say you have some designs on the slab to indicate maybe there's some paneling going on, there's some nice design in going on to create an aesthetic atmosphere. If your slab is too, what's the word I'm looking for, deflects, that means that these, whether it's your POP ceiling, whether it's your hanging ceiling, all of these can be affected. All right. So the idea of the span to depth ratio or a limit to span to depth ratio is to ensure that you end up with a structure that will not deflect excessively, which will lead to damage to some of these key components of the structure. All right. So the finishes, the even your tiles, right? I think in one of the classes that you guys have seen, you see that the tiles are all bulging up and all of that. Maybe it could be a tile issue, or it could also even be that the slab itself are uh, deflecting excessively, right? Okay. Um, so to avoid all of these, we provide a limit. So to avoid um, these, limits are that's on the span to effective depth ratio. Okay? So that we don't exceed certain limits on this structure. So the effective span to depth ratio. So let me say the span to depth ratio. Um, so it's used for both beams and then slabs, right? Let's just take a note of that. They're the same as for beams. So whatever we discuss here can be used for beams, especially when you are dealing with your beam design, with your causeway. All right. Okay, so these are the three things that we have to look at. All right. Um, so I mean, the reason why was one of the reasons why we are looking at all of this is because of the fact that if you compare slabs, slabs would typically be what we usually call slender members. So are usually slender members because of how thin they can be, or their thickness is not that high compared to beams. Um, so yeah, typically slender members, and that means that um, the restrictions or the limits we place on the span to depth ratio is important. Okay, span to depth ratio um, are very important. Okay, all right. So the equation for that, which is the minimum effective depth Um, the mean is equal to the span. So it's equal to span divided by what we call the basic ratio times the modification factors. Okay. So that's how we calculate the effective span to depth ratio. All right. So it means that if you know the span over the ratio, right, then you can determine the minimum effective depth that you need for your slab, right? If it's lower than the minimum, your slab is going to be slender, which means that it can deflect excessively and then have damages to ceilings and floor and also some architectural detailings and all of that. Okay. So the modification factor, we'll look at what this is. The modification factor, mhm. So the modification factor is based on a certain some parameters. One of them is based on the area of the tension steel. So it's based on when the area of tension steel. Okay. And it's typically that the one in the shorter span. Okay. We'll look at what that is. Um, okay. Okay. So that's one. Uh, okay. Let me put. And this is for singly reinforced. Okay. Um, reinforced. Okay. Then, in the case whereby um, if the slab um, has both top and bottom reinforcement, right? So in beams, that would have been tension and compression, all right? At mid-span, the modification factor, modification factor um, is for the areas of seaway of both tension and compression. All right. I think that's the key differences that we are looking at. All right. So let me see if I can pull up some of these modification factors for us to see what they all are. Where do I have this? Okay. So before we look at the modification factors, let's look at the basic ratios. All right. So the basic ratios, so that's a table. If you go to the BS code, it's found in the table 3.9, table 3.9 in a BS 8110. Okay. So this is how it looks like. Just give me a second, and then I'll pull it up. What am I missing? What's wrong with my? Again, just a second. Make sure everything is working quite well. Okay, I'm, st- I'm still recording, so that's good. Okay. So this is the table. Should appear shortly. Okay, I think it's gonna appear. Right. So this table here is a basic ratio table. In this one, it's table 3.9 vs 8110. So this is the what you call the basic and to effective uh, ratio, depth ratio for rectangular and flange beams. Right, so it can be used for both beams and the slabs, right? So depending on what your support conditions are, if your beam is a cantilever, that means that that basic ratio is 7. We'll see an example. If your beam is simply supported, then that ratio is 20. If your beam is continuous, then the ratio is 26. That's for rectangular sections, right? So typically, we also have that for uh, beams with a flange width. So you compare the width of the beam and the width of the flange, and it should be less than or equal to 0.3. Then those factors are appropriate. All right. And these factors also work for span length. Okay, should not be more than 10 meters. Okay, so the highest span length that we can use to, I mean, in terms of these modification factors is 10. Okay, but span length, if span length is greater than 10 meters, so if it's less than 10, then we use this equation. If span length is 10 or more, if span is more than 10 meters, then modify the basic ratio. Okay, and how do we do that? On the basic span to depth ratio. Sometimes, yeah, span to depth ratio by multiplying the whatever value we get over here by 10 over the span. Okay, so that if your span is 12 meters, then it becomes 10 over 12. All right. Okay, and this for the basic ratio. Okay, as in the equation that we wrote earlier. Now let's look at the modification factors. All right. That's one for tension, that's one for compression. Okay. So for modification factors, well, let's say for tension only steel, and these are, again, that's also a table. Uh, Sometimes you think you're sharing screen. It's okay. Everything is fine. All right. So let's look at it. All right. So is it quite a long table? Let me pull it up. We'll see how to use these tables. All right. That's not anything crazy. Um, okay. Let me pull it up. Uh, Where are you? Okay. Oh, nope, not this one. I don't know why it's giving me the wrong thing to copy. So giving me the wrong thing. Okay, go back. Maybe this time around it should work. Okay, great. It's work this time around. All right. So this is the modification factors for tension only. Um, that's fun also for compression reinforcement. Let me just put down also there. So for the tension reinforcements, so the modification factors for tension only steel or tension reinforcement, is found in table 3 point I think 10 in the BS 8110. All right. So it means that um so we have FY of 250 and FY 500. So mostly that's where we look at. Normally for slabs we use mild or high yield, depending on whatever we're trying to do. All right. So these values are gotten using that approach. So there's a way to calculate all of these. I will go through a proper example to appreciate what these modifications factors are. All right. Uh, then for the case of the compression, it is um, so let me put this one as modification factor. So just putting together the data. All right. And an example is I think it's found in the BS score. I think 3.11. This is 3.10. This is 3.11. So table 3.11 in the BS 8110. All right. Okay, great. So these are the modification factors for um, depending on what we are looking at, whether we are looking at what's the name? Whether we are looking at beams or slabs. All right. So let's see an example how this whole system will be of use to us. Um, let's try to, what am I looking for? So let's look at an example of how all of these things would work. So let's see we have so let's say we have a beam, right? This works with beams and slabs, so right? Let's say we have a continuous um, rectangular beam. Sorry. Um, so let's say, and the span is 12 meters with a mid-span moment. So let me put together there, right? Ultimate moment of let's say 400 kilonewton meter. Okay. Um, so this is the cross section of the beam. Our breadth here, or the width is 300 millimeters. Okay, that is given. Um, and then we have an effective depth, right? So effective depth D is given as 600 millimeters. Okay, from the question. And then we have to check the suitability or the acceptability of this particular effective depth. Okay, so that's the 600 millimeters given. We should check if it's acceptable. All right. Mhm. So here, the Fy it's uh it's 460. All right. So that's for the Fy for the tension steel and I mean for both tension and compression. And we have been told that there are two 16 bars in the compression zone. So what it simply means that we have two bars here. Okay. So each one is 16 bars. Okay. There are also some number of bars in the tension zone, obviously, but we don't know how many they are. And the reason is because in this case, since there is some compression reinforcement, it means that we'll go to the table, the modification factor for compression reinforcement thing. All right. Okay. So let's just take a look. Let me move all of these things down. And I need to bring some. I'll call it a new table just so that um, that makes sense. Okay, so let me drag something. 1.5, 2, 3, 4, 6. Okay, so 15, 2, 8, 8. 6. Okay, so let's try. Let me know if you do this. Let me just go back. Okay, great. So let's look at how to solve this problem, and then we'll see what best we can use. All right. So since it is a continuous rectangular beam, all right, that's what it says. Let's first find our basic ratio. Okay, let me do that in caps. So in basic ratio, we go to table 3.9. Okay, so for basic ratio, see table 3.9. And from table 3.9, which is what I have over here, for a rectangular section, which is continuous, we use 26. Our basic ratio is 26. All right. Now let's check the length of the beam. Right. So the beam has a length of 12 meters. All right, which is more than 10 meters. So it means that we need to modify the basic ratio. And that will be what? The basic ratio times 10 over the span. Okay. So this is going to be the 26 that we chose times 10 over a span of 12. Okay. So this will give us 21.7. Okay. So because the span is longer than 10, it means that our ratio has now been reduced to 21 instead of 26 because of the fact that we want to make sure we limit damage to finishes on the structure. Yeah. So let's look at the tensile. So the tensile, let me just use black. Let's look at the tensile reinforcement modification factor. Okay. Let me say MF. All right. MF means modification factor. Okay. So that I don't have to write this long thing. All right. So M over BD squared will give us our M was 400, so times 10 exponent 6. Our B is 300. Our D is given us 600. So 7 squared, we get 3.7. All right. So let me bring in a table similar to what we had earlier. It's the same table, just that because this one, I'm using FY of 460. The previous table didn't have that, but this one has, so I can use that one for my computations, just so that everything makes sense to us. All right. Let's try to wait for things to load. Takes a bit of time sometimes for things to load. But I think it has. All right. So and I know where to place items. Okay. So let me use this table. Yeah. The same as. So this is for this is like table 3.10. All right. Okay. Great. So if we come to this table, which is the sorry, the tensile table. So we have 3.7. Our FY is 460. So it means that we will be looking at this zone. All right. We're looking at the last bit. So if FY is 460 and we got 3.7, um, so our our 3.7 will be somewhere here. Okay. So we are looking at between 0.95 and 0.87. All right. And this is pretty much we do some bit of interpolation. All right. So if we do the interpolation, you will realize that your modification factor for tension reinforcement will be 0.89. So the modification factor for tension reinforcement will be 0.89. We've gone through how to do some of these computations already, so I'd advise that we just look at it. It's the same thing, nothing really has changed. All right. Um, all right, so now let's look at the compression reinforcement. Um, so with that one, we need to find this equation 100 AS prime over BD. All right, where it's 100. Since there are 16, 216 mm, 216 mm bars, the area for 116 mm. Let me put that, let me just put that on the side, maybe a different color. So area of one 16 mm bar, it's about 201 millimeters squared. So if there are two, that'll give us 402. All right. So 100 times 402. B is 300. D is 600. All right. So this will give us 0.22. Okay. So what do? We come back to this table, this big table over here. I think, yeah, it should work. Nothing should change. So let me just bring the table back now here so that it makes it easier to follow what is happening. Then you paste it. So I just put it here. Okay, great. So we got 0.22. So we are looking at somewhere 0.22. So somewhere, so 0.22. Okay. So our factor will lie between 1.05 and 1.08. Okay. If you do the calculations, you'll realize that from table on the left, the modification factor for compression reinforcement will be 1.07. Okay. So once we have that, now we can determine our span to depth ratio, right? Um, so it becomes our limiting span, which is all that we'll be trying to do on this file, and put into this box here. It would be so we have it is a modified. Okay, let me just take the box out so I can. It is a modified basic ratio times the modification factor tension and then times the modification factor compression. Okay. So this will be equal to so let me just okay. So this is going to be 21. Let me ask 21.7 times 0.89 for the tension, then 1.07 for the compression. All right. So this becomes 20.7. So this 20.7 basically is your effective and or span to effective depth ratio. So span to effective depth ratio. All right. So this is the limiting value, right? We cannot go above 20.7. We can go below 20.7, or we cannot go above 20.7. All right. So let's calculate what we got from what's the name? From the size of the beam and see if we are adequate or not. All right. So what we provided, right? What we provided was that our span to depth ratio that we provided was the span was 12 meters, so it becomes 12 times 10 exponent 3, and then our depth was 660 millimeters. All right. So this will give us 20.0, or let's say 20, I believe. So since 20 is not greater than 20.7, we can say that, okay, then the deflection requirements are satisfied. Right. So this is like, in simple terms, how we determine all of that in here. Okay. Um, So now let's look at um. Okay, let's just take a break and then we'll come back and look at the solid spans, like how to actually now design spans of beams. I'm sorry, slabs. All right.